Hello and welcome to Biousage Lessons. Today we are going to have two more examples of homeostasis, or maintaining the conditions, the state of your body constant. Homeo, the same, stasis, state. So two more examples of homeostasis. One of them, the homeostasis of gases, oxygen and carbon dioxide. As you know, oxygen is very important for us to do aerobic cell respiration, basically for us to make use of all the fuel we have inside of us, all the organic molecules that we have inside of us to be able to produce movements, to pump the stuff in our cells. Everything that requires energy in our body is going to be requiring these organic molecules to be suffering respiration. And the main cell respiration to do, because is the one that produces more energy per gram of organic molecule, is the aerobic cell respiration. So we need oxygen desperately in our cells. If your brain, for example, stay without oxygen for 20 seconds, you faint. Actually, some people faint in 5 to 10 seconds. So oxygen is extremely important. And carbon dioxide is the byproduct of the cell respiration, and it's extremely toxic for us, and we need to get rid of that. So maintaining the oxygen and carbon dioxide in a constant way, it's quite important. That's why you have our ventilation system to get the oxygen in and carbon dioxide out. But if we change the way that we are spending our organic molecules, that we are doing cell respiration, we may need more oxygen, we may produce more carbon dioxide. Therefore, we may need to speed up the way that we get oxygen, we get rid of the carbon dioxide. So basically, when you do exercise, that's the way that we usually are going to be consuming more oxygen, producing more carbon dioxide. Carbon dioxide goes up, oxygen goes down. So what? What is your body going to be doing in that way? Unfortunately, our body has no sensor for oxygen. We don't manage to know if our oxygen level is getting low. So basically, if dependent on your body to be sensing the oxygen level, the oxygen could go down and down and down, and you wouldn't notice it, and you would faint. So therefore, the sensor should be on carbon dioxide. But we don't have carbon dioxide sensor as well. What we do have is a sensor that will sense carbonic acid, which is carbon dioxide in our blood. When you get dissolved over there, it becomes carbonic acid, which is an acid, and therefore it's going to be reducing the blood pH. We don't have carbon dioxide or oxygen sensors. We have a pH sensor in the subclavicle blood vessel, just under here, your collarbone. You have this pH sensor that senses when the blood pH changes, and therefore, if the blood pH gets acidic, so if the pH goes down, that means you have way too much carbonic acid, that means you have way too much CO2. So that's the way that you're going to be sensing. So the subclavicle pH sensor senses the blood pH. If it's acidic, it sends a nerve signal to the medulla oblongata, the bottom of your brain, that regulates the things that we do automatically, like heart rate and ventilation. And this is going to be telling your body, increase heart rate, increase ventilation, and then we are going to be exchanging gases faster, and then carbon dioxide will be reduced, the pH will go back to norm, and we have that fixed. And in the meanwhile, when you are dealing with carbon dioxide, it also deals with oxygen, because if carbon dioxide goes down by ventilation, by exchanging more gas, then oxygen, of course, went up as well. So then we deal with this. So by doing the homeostasis of carbon dioxide, we are actually doing the homeostasis of oxygen, just together with it. But even without sensing oxygen, we have it regulated inside of us. This is the homeostasis of carbon dioxide and oxygen by negative feedback of carbon dioxide. Okay? And one more example of homeostasis, very important for us, regulating glucose. Why do we add glucose? Why do we add sugar to fruits to make jam? Yes, it's because jams is delicious, but also because when you add sugar to juice or to fruits, we make it very, very, very sweet. Pathogens cannot grow in there. You kill the pathogens because too much glucose is toxic. So the same will happen with us. Okay, jam will taste good, but jam kills the pathogens. Now the sugar. Too much glucose can be toxic for the pathogens. Too much glucose can be toxic for us. So if you have way too much glucose floating around your body, you may end up having some problems, like for example diabetic foot. Some damage that you make in your foot, it doesn't heal, and if this goes on and on and on, you may end up having to amputate your feet because the tissues don't get cured because of too much sugar. This is what is called diabetic foot. Uncontrolled diabetes can lead to this. So let's talk about eating. Yes, sugar is good, sugar is important. Our body craves sugar. We are always wanting to be eating sugar. So what happens to the blood glucose when we eat? Usually when you're fasting, the blood glucose would be around 80, 90, below 100. So the norm is fasting, the blood glucose should be kept below 100 milligrams per deciliter. Yes, it's a weird unit that the healthcare providers they use, but yeah, that's the unit that we use. 100 milligrams per deciliter is the norm. It's below that, okay? 80, 90, 100, that's the normal stuff. When you eat, the blood glucose rise. Yeah, you're absorbing glucose through your digestive system. It gets into your blood and blood glucose goes up. And if we don't deal with that, it could rise and rise and rise. It could go up to 200 before you start spending it. And then you eat again, it can go to 300, 400, 600. And then it goes out of control and then you have a big problem. So to avoid that happening, we have a negative feedback mechanism that can control that, because high glucose can cause several different problems. Tissue damage, as I just showed you before, can cause you circulation problems, can lead to blindness, can lead to kidney malfunction, can lead to coma, and even can lead to death. So too high blood glucose is not good. So let's take a look on how we control that, how our body is going to be avoiding blood glucose from growing too high. So we ate, blood glucose should rise and rise and rise, but the liver, the muscles, and the adipocytes are going to be taking in glucose and are going to be storing it. But they only do that if they are told to do that. So basically, your blood glucose has to signal your body to tell your liver, your muscle, your adipocytes to take in glucose and store it in the way of glycogen. Okay? For you to do that, we need a hormone. We need a mechanism. So basically, what's going to be happening is that if glucose goes up, your pancreas releases a hormone called insulin. So insulin is released by your pancreas that senses glucose level, and then insulin tells your liver, your muscles, your adipocytes to absorb glucose and then take it down. So basically, it is going to be making it to move down. Insulin is the one that's going to be doing that. Okay? If the blood glucose goes too low, that can also be a problem. Low blood glucose, then of course it's bad. We don't have enough energy to power everything in our body. So we have another hormone also released by the pancreas that senses low blood glucose called glucagon. And then glucagon is going to be signaling your liver to break glycogen and release glucose in the bloodstream, regulating glucose level. So basically, it's going to be putting the glucose up again. If we put all this here together, let's see, glucose goes up, you release insulin, insulin makes glucose absorption by the liver, muscle, adipocytes, which makes the glucose to go down. If the glucose goes too down, then glucagon is released by the pancreas, and then is going to be making glycogen to be broken in the liver to release glucose in the blood, and then the glucose goes up. This is a negative feedback mechanism sensed by the pancreas, controlled by the pancreas through the way of the hormones insulin and glucagon. Okay? So, let's take a look on how this goes on a regular day. We have the blood glucose that is around 100 or below 100 ideally. You have your meal, the meal is over here at the time that we call 0, and then blood glucose goes up. But instead of going very high, you release insulin, and insulin is going to be making your blood glucose to go down. So it goes down to normal, way too down. It went below the 100, so you release glucagon. And then it goes up, it's going too high, insulin, too low, glucagon, too high, insulin, too low, glucagon. And then you keep your blood glucose by regulating in a very fine-tuned glucagon, insulin, and you keep it around a certain level, usually below 100. This is how we control blood glucose, okay? And just for you to know, glucagon and insulin are produced by 2 cells in our pancreas that we remember with this mnemonic GABI. I had a student that created this. She was Gabriela, and she created the GABI mnemonics for us to remember. Glucagon is produced by the alpha cells of the pancreas, and the beta cells of the pancreas produce insulin. So GABI will make you remember that glucagon is produced by the alpha cells and the insulin is produced by the beta cells. So here, just for you to have an idea, the beta cells are there, the alpha cells are here. Those are the cells that are going to be producing insulin and glucagon in the islet of Langerhans of your pancreas, okay? So this is the guy. The pancreas, therefore, became even more important than you thought it was in digestion. In digestion, you see that it produces many enzymes, and here it also produces hormones to control your blood levels, okay? So this is your pancreas. If we have problems with our pancreas, if we have problems with these hormones, you can have diseases called diabetes. So diabetes is lack of control of some substances. The classic diabetes is the lack of control of blood glucose, diabetes type 1, diabetes type 2, and the gestational diabetes, the pregnancy diabetes. There are 3 diabetes that are related to lack of control of sugars, okay? So it's basically the difficulty of control of blood glucose in your level, okay? Symptoms of diabetes is tiredness, increase in urine volume because you start peeing glucose and start to pee a lot. Of course, if you're peeing a lot, then you feel thirsty. You feel hungry because you're not keeping glucose in, you're putting it away. And there are 2 types of diabetes that are the classic ones. Type 1 diabetes is the one that develops in the infancy. Type 1 looks like an eye. Infancy is the one that triggers before adulthood. So type 1 diabetes usually triggers before the 20 years old. So all of you here, you are almost getting too old to trigger diabetes type 1, although it can happen. I had a 17 years old student that developed type 1 diabetes. Type 1 diabetes, it has a very high genetic influence, and basically it's an autoimmune disease where your body starts fighting your pancreas and start destroying your alpha and especially your beta cells, so you stop producing insulin. So it's the one that you don't produce insulin. And if you don't produce insulin, you have no way of signaling to your liver, your muscle, your adipocytes to take in glucose to regulate that. So this disease that's caused by yourself destroying your own beta cells, it's autoimmune, is going to be causing you to have problems controlling your blood level. It's inheritable and it is dependent on insulin. This is the insulin dependent diabetes. If you have type 1 diabetes, you need to take insulin. You eat insulin, eat insulin, eat insulin. Because of that, it's quite manageable, because if you learn to control your blood glucose with insulin, you can have a quite normal life. Nowadays, we have technology that you can have sensors instead of doing this pinching of your finger to test your blood. You have a sensor that can measure blood levels up to 15 days, so you only do that for 1 time, 2 times a month. And you can even have a little pump that can automatically pump insulin along your day. So you're going to be eating and the insulin is going to be released, so you can have a pretty normal life. Okay? Type 2 diabetes is not the infancy one, although it can happen in children. Type 2 diabetes is a diabetes related to overusing the insulin system. So it's very common in elders because old people have overused this over their lives. And also it's strongly related to obesity. So obese people can develop type 2 diabetes. Type 2 diabetes, it's not insulin dependent, it's controllable with diet. Okay? It's the one that you produce insulin, but your body becomes insensitive to insulin. So basically you still have your insulin, but your body is stopped listening to it. It's very fortunate that you still have insulin, but because it is your body is not listening to insulin anymore, you have to control the diabetes with diet and with exercise. So basically you have to avoid eating too much sugar, to eat it in small portions, to have it raised slowly, and then you exercise, you make it go down. So it's totally manageable with diet and exercise. The problem is that usually people that develop diabetes type 2 are people that have overused the system, have abused of sugars all their life, and it's quite difficult for them to say, okay, now I'm going to be controlling this with diet. How are you going to be controlling diabetes with diet for someone that that became diabetic because they have eaten too much sugar all their life long? So it's quite difficult to control this. But it is manageable. People just have to learn how to control their diet and do exercise, and they can have a quite normal life. Okay? Just to illustrate to you what I showed you before, this here is the sensor that you can put in your skin. So we are going to be talking more about that in class. Okay? This is the little thing that you put there in your body, and then you can control your blood glucose. Nowadays you have technology to make type 1 diabetic people's life much more comfortable. Okay? So I hope you have enjoyed this class. We'll discuss more on this in class, and bye bye, see you soon.